Maybe someone someday wishes how do you think, is it possible that someone someday, oh, wait 1 second, not this, wait 1 second, we need mark you here. Yeah, and I'll need to, yeah, save. 1 second, I will save. In a learning system. I'm not sure anyone will watch it, but maybe yeah, switch off. Previous lecture got 5 views. Gibbs paradox 2 views. It's more, it's a lot. Okay, I want to save this, it will be needed later. And here is a good blackboard where I can draw small schematics. I have a generator of ideal harmonic signal. One half of nanofarad coil capacitor. It's adjustable. It's 1 nanofarad. And coil, where is my coil? What's written here? 7.45 millihenry. I have here yellow signal is taken here and blue line from the coil and capacitor junction point. Yellow line, blue line, capacitor, coil, first capacitor, and signal source. Maybe I can do it this way. Yeah. Whoa. Let's turn the camera a bit to make it. Yeah. I would like to draw your attention to these 2 digits. It's an effective value of the first signal and second signal. Look what happens when I change frequency. I'll need to change scale. Look what I got. Input, half a volt, 460 millivolts. Yeah? Output, 12.7 volts. Yeah, 12.7 volts. I'm changing frequency. Can we explain it? Maybe it's magic?
The second capacitor works here.
What's the effect of capacitance change? Effects observed only on one particular capacitance. I can also change inductance. I have this ferrite block. It's a good conductor for magnetic field. Adding it to the coil, I will increase magnetic conductance and thus increase inductance. I can compensate presence of magnetic block with the capacitance change. Do we see something familiar?
What's the difference between the adjustable capacitor and the normal?
In capacitance, this one fixed. I just needed to, I can show it without this capacitor. I just need to separate network from the low output impedance of generator. My generator has output impedance only 5 ohms at this moment. So to isolate circuit, I use this interim or sequence capacitor. Magic happens here. Maybe something familiar. Something like this should present in a theory of in the basics of electric circuits. You missed your magic. We have a magic here. Energy from nowhere. Half a volt, okay, 400 millivolts, 700 millivolts, and in one particular moment, we have 12 volts from a half of volt. Huh? Something familiar? Basics of electrotechnics. If this is point A, haven't you seen something like imaginary part of conductance A 0 equals to 0, something like this? No? Ooh. Someone sent me a message. let's try to dig deeper. At this moment I have voltage from nowhere, isn't it? Generator supplies 400 millivolts, yeah? And I get 12 volts. I will not help you until I finish my question. I will not help. Where is my blah blah blah? Okay, I can draw a small schematics. I have source here. I will have coils. Oh. Ну а что я сделаю? Так. Okay, what I coil here, capacitor here. I will have also resistance and earth. Ah, something like this. Can I switch? Make it bigger. And let's assume that we have current as a function of time. Nice network. Oh, hello. You're missing magic. We are getting energy from nowhere. 400 millivolts at the input and 12 volts at the output without any battery or active energy source. What shall we do with this network? We can write a Kirchhoff voltage law, or second Kirchhoff law. Can? Can. What it will be? Such a nice network. Resistance multiplied by current plus inductance by current first derivative plus sum of all charges will make us capacitor's voltage equals, am I right? Voltage drop on resistor, on active resistance proportional to current. Voltage drop on a coil will be inductance multiplied by rate of change, and voltage on capacitor will be sum of all charges. If this is equal to the source voltage. How to solve it? I need current. I need to get rid of integral sign. This means what I need the first derivative of this. And also, to make it look like standard, already solved differential equation, I will get the second derivative. I need it without a factor. This means what I will need to divide by inductance. This will yield me what I will get. I will get second derivative of current plus first derivative of current plus 1 against equals to the first derivative of the power source. Why this is done? Have you seen such equation somewhere? It's an equation of oscillation. Thin object like guitar string oscillates according to this, and it is solved. Key moment, this equation already solved. Actually, in transients theory, there is one basic idea. We need to separate free components from enforced or infinite time components. That's the idea. I'll try to illustrate. Very simple. I have, let's say, something like capacitor, and switch will disconnect at time 0. 1 capacitance is a network. And for example, this is our voltage. Let's draw something. Time. Can we say voltage before the switch is opened? What will be the voltage before 0 time? Before switch is opened, what is the voltage here? Come on! 0, of course. 0. And next moment, what will be voltage at, let's say, infinite time? Can we say? Infinite time. Capacitor will be fully charged. Yes? Its resistance for DC will be infinite. Yeah? So capacitor out, and we have divider of two resistance. Current through this divider will be E divided by sum of resistance. Isn't it? And voltage will be current multiplied by this resistance. So at infinite time, let's say, we will have E L2 divided by L1 plus L2. This is infinite time mode or enforced mode. What we will see after transient is ended. And what between them? Pre-computation and enforced. Between them will be a free component. One F power. Here is the core of such lines. Actually, it will be U infinite minus U infinite multiplied by simple U infinite multiplied by this. Here is a free component. So idea of transient is to separate free components, transient itself, and enforced or infinite time mode or infinite time component. In our case, infinite regime is very simple. But we need free. So to find the free component, we need to solve a differential equation. F means free component. Square plus double alpha EF plus omega 0 square EF equals to 0. Here, alpha being F divided by double A is a decrement factor, and omega being 1 divided by square root of LC is a free oscillation frequency. Actually, it's an oscillation frequency. If you try this imaginary part of input resistance equals to 0, you will get the same frequency at which capacitor reactance is fully compensated by coil or coil inductance when they are equal. It will be moment when 1 against omega t equals to omega a. As I mentioned, such type of equations are already solved. And solution, free current as a function of time will be I1 a power the one time plus I2 a power lambda time, where lambdas are roots of equation and these two constants are dependent on the circuit state at the computation moment. They are so-called results or product of border conditions. To get lambdas, just need to solve an equation, lambda square plus double of lambda plus omega 0 square equals to 0. This will get you what? Minus alpha plus minus square root from alpha square like plus minus omega square. These are frequencies possible. Well, okay. Character of the process is defined by lambdas and a border condition or starting condition by these two constants. To make more compact, I will introduce beta as a square root of alpha square minus omega 0 squared equals to square root of resistance squared divided by quadruple inductance square minus 1 against LC. So, free current as a function of time will be a power minus alpha I1 a power beta plus I2 a power minus beta time. Full current is sum of free component plus and forced component. Good. Now to make things easier, I need example. Now we have some mysterious constants and mysterious roots. Let's take a simpler network. Why simpler? We need a network with a zero border condition. It will be easier to, let's say, determine these constants. Let's take a network like this. I have DC source, capacitor will be charged from it, and then coil resistance switched at the time 0. Coil capacitance. What's good here? This is current equals current at 0 equals to 0. This means A equals to what? To minus E. to minus I1 and equals to minus E0 divided by double beta A. We have a good border condition. We got border conditions and we can write, so free current as a function of time will be minus E divided by double beta L E power minus alpha E multiplied by E power beta minus E power minus beta L. Coil voltage free, let's say coil voltage free as a function of time should be A F by time, or it should give us, let's say here, E0 Y, I don't need this, divided by double beta A power alpha multiplied by alpha plus beta A power beta minus alpha minus beta A power minus time. It's called this. It's a coil voltage. 1 second, I will. Wait. Oh. Wait. I see here should be minus and here plus. Yeah, no, it's correct. The same. It's a coil voltage. 1 second, I will write down the capacitor voltage. But this, who trusts these formulas? We need to see it alive. One moment. Free capacitor voltage will be A divided by double beta A power of multiplied by alpha plus beta A power beta time minus alpha minus beta A power time. Yeah. How can we get all this visible? At this moment, it's just some unclear equation, isn't it? I will use bit different setup, so we will be able to watch it. I will use pulse generator, producing 1 microsecond pulse. Each 1 millisecond. It will charge capacitor and discharge over separated part of the network will occur. This means what this process will repeat every millisecond. And we will be able to watch it as we want. Okay, I need to disconnect this one. Better I will take capacitor load. 1 second, I will assemble my network and we will investigate this no longer needed. And we will be able to investigate free oscillation without any disturbance.
How do you find the loss during capacitor charge? There will be part which will flow.
Good question, very good question. Yeah, we actually we need insulation losses and active losses in capacitor. Let's say veins forming the capacitor. Let me demonstrate one thing. I'll speak a bit about it. But actually, there is a special measuring device called sharing bridge. With the help of sharing bridge under high voltage, we can measure losses in the electric. They are hidden under Tangens Delt idea. It's for ideal capacitor, current and voltage form an ideal 90 degrees. Distance between them makes active losses in insulation. But losses from current they are measured with the help of calibrated resonance network. There stands a device called Q meter. But we don't know what is Q. We will. 1 second. Okay, minute. Everything should go in sequence. With Q meter, you get overall losses for capacitor. So you need to first, if you need to separate losses, at first you measure with the sharing bridge losses of the electric material, and then you get with the Q meter you get total losses of capacitor. I need resistance box. I need resistance. How can I without resistance? I need a lot of resistance, so I will use 2 boxes. Here. Here. Here is the ground. For example, I can don't need the point. Please. high potential. Gray one for low potential. And white. Oh, I have one. And this one goes here. That's good now. From the you will charge my capacitor. Something goes here. 1 second. I need one more. I need a good ground connection. Example here. Resistance now set to 0. Time scale like this. At this moment we see this let's say we see it as a yellow line. I may repeat my formula. Where are you? I don't need a current. Now it's E divided by double beta, A power alpha E. Alpha is a decrement R divided by double A multiplied by alpha plus beta, A power beta minus alpha beta, A power minus beta times. This equation is this nice yellow line. What do we see in it in formula? This one, what it means? Decay. 1 second, I have mechanical analog. Decaying. Why? Because energy amount system received with the heat is limited. System is dissipated. The same thing when this pulse generator sends 1 pulse, it's like heating the tuning fork. I'm charged, capacitor charged, and no more energy supply. System goes down because no outsource of energy. And this decay is determined by term resistance divided by double inductance. If I add more resistance, okay, it's low. See, I'm adding more resistance and we see faster decay. It's like dumping. My finger is the same, it consumes energy as resistance box. But these two betas. What's hiding? Under the beta. Beta equals to square root of alpha square minus omega 0 square. Yes? We have two possibilities. One, alpha is greater than omega frequency, and other, omega greater than alpha. If alpha greater than omega, beta will be real. Yes? And if omega greater than alpha, what will be beta? Imaginary. Beta will become an oscillation frequency. There is a moment when active resistance is smaller than double wave or characteristic resistance, or is lesser than square root L divided by C. It's a characteristic, some call it wave resistance. Take a look. Now my resistance box is set to 0, only resistance remains is a coil resistance. I will increase resistance. What we see now? Before I increase, can I change the scale? Is it sine? Harmonic oscillation, like a tuning fork. I will increase resistance. Decaying, decaying, decaying. Add more resistance. More resistance for the gap of resistance. Here, 1 second. Here it is, so-called critical resistance. When they are equal. At this moment, alpha, the decrement, is equal to frequency. And we see 1 pulse. Increasing alpha. See what happens? Our process become aperiodic. See? No, it's non-periodic signal. Lesser resistance. Shorter, shorter, shorter. And our process have a character here of decaying oscillations. We have an oscillation contour now. Increase resistance, aperiodic network. Beta, at this moment, beta are real. Resistance or active resistance is greater than double characteristic. Non-periodic, periodic. Free decaying oscillations. Changing capacitance. See? Frequency changes. Inductance, it's the same thing. Frequent, where is my ball? Inductance change. I increase inductance, this means what? Oscillation frequency decreases. Why? Because system is capable to store more magnetic energy. More magnetic energy means greater inertia. Greater inertia means slower oscillation. So, if I can if R lesser than the square root L divided by C. 1 second, I need double. I need to double here. R greater double square root. In this case, lambdas are imaginary. So, beta square root alpha square omega 0 square will be minus simple j omega f free oscillation frequency. We will see decaying oscillation. This line is determined by alpha decaying. On the opposite side, we will see non-periodic process. I would like to draw your attention. I will switch to make it bigger. The red line shows Fourier transform results of the yellow signal. Now we have free oscillation mode. And all energy is, let's say, concentrated on one particular frequency. What frequency? Frequency of free oscillation. If I increase active resistance, see what happens. Do amount of energy changed? No. Amplitude of pulse remains the same. Length or time of pulse remains the same. Generator supplies the same energy. But how this energy is distributed? You see? It's a decaying row of frequencies as we saw on our previous. As a distribution for a non-periodic signal. Periodic mode, all energy concentrates on one frequency. Non-periodic, it's, let's say, spread over the wide frequency range. It's worth to know this. What would I write? If we have an oscillation contour, frequency of free oscillation is bit different from the frequency indicated by zero of imaginary part of input resistance or conductance. Real free oscillation frequency is theoretical omega 0 multiplied by 1 minus resistance squared divided by quadruple characteristic resistance. Difference is not huge, but it is. Losses in contour shift free oscillation frequency from theoretical. The shift isn't significant, but it's present. In case of free, so if beta equals to j omega, free, I started to free current will be E divided by omega 3A, A power and alpha sine omega. Current will have a form of decaying sign and voltage is 2. Sorry, I need to switch. You see, it's a sine, it's decaying sign. If it will be a constant power supply, not pulse, oscillation also will be constant. But here to show the full process, I'm using a pulse supply. To characterize, let's say, quality of this oscillation system or resonant system, the decrement is introduced. It's active resistance divided by wave resistance or by square root. Who is drawing square root? L divided by C. It's characterized losses in a contact. This decrement unit isn't widely used. Widely used its inversion, Q. Q from quality. Q1 divided by decrement. It's characterized quality of oscillating system. Quality of our oscillation system. Actually, it's a rate. It's a rate of reactive ratio between energy stored in reactive elements. Let's say how the system gets energy. Generator charges capacitor. So if at each moment of process, energy stored in capacitor can be compared to energy lost in active resistance. Fewer losses, better oscillation. We can use such system in a mode of constant signal, like pushing it all the time. It's like pendulum pushed all the time. For example, series oscillating system. Here, harmonic with the frequency omega. Coil capacitance resistance. S A. Input resistance or A to ground will be R plus omega L minus 1 divided by omega C. Yes? Depending from frequency, it may be capacitive or inductive, but at the one particular frequency, we will see what? 0 in imaginary part. This term will become 0. Yeah? At a frequency 1 square LC. It's a frequency of resonance. And current in contour will reach its maximum. Because only these two compensates and current will reach its maximum determined by remaining active resistance. It's so-called voltage resonance or resonance of voltage. So, will be E divided by resistance. At the omega 0, will be equal to and equal to what? A rho divided by R or A cube. If you have a contour with a good quality, for high frequency, quality of 400 is reachable. You see quite a high voltage. For ordinary coils with quality factor of 100, you can get 100 times more voltage. But there is one problem. The problem is equivalent quality or overall. Wave divided by thin resistance plus internal resistance of voltage source plus, if we have load, we need to introduce it. This is a load. If we would like to take some energy from the contour, no. So it is better to use sources with low internal resistance in case of voltage resonance, if we want to use it. How can we use it? Generally, such networks are used as selective networks. To separate a narrow band of frequency or to extract or cut band of frequencies. For analysis, often used relative frequency, it's simple frequency shift minus omega 0 or relative frequency shift. It will be square divided by frequency square. It's a relative frequency shift, or very popular is so-called my God, it's a common frequency shift. It's relative and what's the name? Divided by omega 0 minus omega 0 divided by omega. And quality of contour. Wait, I would need to shift. Frequency shift. So simple frequency shift, relative frequency shift, and kind of global or common frequency shift. Resonance characteristic. particular system usually is drawn as a current at the moment divided by current at omega equals to omega 0 or at resonance point. And it will be 1 divided by 1 plus c squared. It will produce a resonance characteristic for the let's say voltage resonance contour. It is not important do you take voltage from coil or from capacitor. Transfer function equals to Q omega 0 divided by omega square 1 plus c squared. Or current divided by resonance current and multiplied by Q and frequency divided by resonance frequency. All this chart have the same form, something like this. It's around at frequency 0 and spreading depending on contour quality. At the resonance point, this transverse factors equals to contour quality. It's for sequence contour. Can we do it for parallel? The same story. Source with R internal, capacitor, coil. First. Voltage. I can show it with a voltmeter. This voltage can be characterized at resonance point, so at frequency equals to omega 0. Characteristic will be the same. 1 divided by square root 1 plus c squared. Same thing. Approximately it's approximately 1 divided by square root 1 plus double Q delta omega divided by omega 0. It's an approximate. We will see the same characteristic as for sequence resonance. But one moment. Equivalent quality will be characteristic resistance R coil plus R capacitor plus rho squared divided by generator internal or source internal resistance. This system works better on high input resistance or high output resistance of source. Here's the difference. Characteristics. In general, transfer characteristic L equals, it's when we take voltage from coil or capacitor, not important, it will be Q omega 0 divided by omega square root 1 plus frequency shift square. What should I do? I need to show it. How can we make this visible? I will send someone to help. Простите, могли перезвонить сейчас занятие? We need to make it visible. At this moment, all this is kind of blah. I can use a special device called analyzer of frequency amplitude characteristics. Idea which высажу figure. If we take a generator of voltage like this will be better. At this stage, voltage will be proportional to time. Yes? Let's take it voltage and use it to control by frequency of harmonic signal generator. Also, we will need stabilizer to get this generator voltage constant. And this voltage let's use as an input signal for some network. This is stabilizer to ensure generator voltage is remain unchangeable. Nice. Output to the amplifier, and to receive a chart of transfer function absolute value, we will need an X function. Now, let's take cathode ray tube. Horizontal movement will be from this generator. Vertical movement as an EPS figure. What we will get? Horizontal movement is a time, but it's the same time in which this generator frequency changes. The so-called sweep generator. Frequency up, down. Up, down. So it scans frequency range. Horizontal movement will correspond to this scan of frequency range. And vertical will be network response, absolute value of network response to the constant voltage. Constant by amplitude, but variable by frequency. Yes? I will kill someone. Jā, un es parakstu. Es jums esmu jāpaka parakstu. Nu jā, labi, man tāds nodarbība, bet tur būs jautājums ar Pēteru. Vai dekāds saskaņa, bet būs jautājums ar Pēteru. Es uzreiz brīdī. Labi, man iesturās jau. Ai, nabagais cilvēks. This guy is making suicide. Trying to defend his thesis, but switching commissions. I don't think it will work. Let's go. something alive. It was a mistake. Okay, what I got here? And I go here to make it visible. I made a resonance network. Case coil. Very good quality coil on ceramic base, made of high quality copper. Here I have variable condenser. It rotates. And small rheostat for the active resistance. Let's see response of this network in a frequency space. Hello, hello. Yeah, and can you see it? No. I'll bring camera close. I'll bring camera closer. Not ideal. 1 second. Maybe. Problem with such device. Always say a low contrast image. Yeah. Can we see? I know. Direction. Like this? It's okay? Here is characteristic. From the table. On the horizontal axis, we have frequency. Here we have frequency. Here we have actual absolute value of transfer function. And it has a character of resonance curve. Do we see it? Yeah. What can we say about such network? We saw network low pass filter suppressing high frequencies, yes? We saw high pass frequency suppressing low frequency. This one is a band pass network. It passes a range of frequencies. Let's change something. What can I change? I can change, where am I? Active resistance. 1 second, I'll switch scale. See what happens? Active resistance increases losses, diminishes quality Q, and characteristic goes down. Meaning what? This network, its resonance, not so good. You see? I'm increasing resistance. Another change. I can change capacitance. With increase of capacitance, what do we see? Resonance frequency goes down. But what with quality? See what happens with quality? it also goes down. Why? Losses in capacitor vanes introduce active resistance. So even small resistance change resonance characteristic significantly. Why? Because it's a square. Okay, what else can I change? I have two small bars. Which one? This one. It's a ferrite. Material with a good magnetic conductance. What will be the effect if I introduce it to coil? Magnetic conductance increases. Yeah? Inductance also increases because coil can store more magnetic energy. More magnetic energy means more inertia. More inertia means higher or lower frequency. More inertia. Is it easier to push something heavy? No. So frequency decreases. And what will be with losses? They will decrease because losses will decrease because we need to spend an energy to shift magnetic domains in the ferrite. Higher losses, lower characteristic. Take a look. See? Frequency shifts down and goes up because losses, I have increase in loss. On opposite side, I have a brass screw. What will be if I introduce a brass screw? It's a short circuit contact. It will increase frequency. To show effect, this object, aluminium pipe, small piece of aluminium pipe. It's a cylinder. It introduces a short circuit, kind of secondary winding in a coil. You see what happens? Frequency increases because it absorbs magnetic energy. And of course, the losses will be high. Now you saw a resonant, kind of a resonance characteristic. I may switch scale. Oh, sorry. Oh. You see small marks on the line? I hope they are visible. Each mark is 1 megahertz. Oh, you see, they are disturbing. Each a megahertz. It's to understand the scale. So from side to side, it's 1 megahertz. Okay, it is. We saw a resonance characteristic. Switch off. In internal language or jargon, such system called second degree system. Why? Because characteristic equation has two roots. A periodic system has one root, non-periodic. Oscillating system has two roots, and may work like this. Now, I think source of magic is no. Such network, what's the purpose of such network? To act as a selective network in communication technique when we need to separate a band, short band of frequency from all possible. In our case, in case of power engineering, we analyze such network, let's say, in negative way. Overvoltage, resonant overvoltage, especially it's painful, let's say, area, earth fault in a city networks. When all isolated network capacitance discharges to the fault place. It's for master program. Earth faults are not for bachelors. Okay, I think it's enough for today. Maybe some questions? A lot of resonance. Next time we will see complex system resonance. This part, I wonder why you don't have it in theory, in the basics course. Voltage and current resonance should be in course of electrotechnic basics.
Of course. The resonance we have.
What? Strange. Until zero frequency, you don't have. You have correct. Or you have. In early time, there was a characteristic on depends on coil inductance, on capacitance, for voltage and current resonance, and all without transfer characteristic and without differential equation. Just see, and without frequency shift.
Just the resonance of the voltage and the current.
Free part should be in circuits theory. Also without transfer characteristic. Well, it is as it is. Theory of signals starts where the circuits theory ends and goes actually till the gates of hell. Okay, we have 0 viewers, so I can end the stream.